this is problem 7, and we're given a situational problem very similar to what you'll see on an exam, and in this case it involves an algorithm, something more abstract. Now, most algorithm questions boil down to how best to model the situation to a more abstract problem representation where you know the answer, so you can apply the answer to multiple different instances of that same abstract problem. So a similar example is you have two very distinct cities, SF and New York, and you can model these two cities as big cities. And big cities share certain properties like density and whatnot, and they also have general solutions such as biking, or accommodating bicyclists, or having a rail system. So these two are very similar. You're trying to fit the stable marriage problem to this situation. Now you can think of the stable marriage algorithm as a function of two arguments, list of preferences of men and list preferences of women. And now a question naturally arises, who should be the man and who should be the woman? And so the complexity comes into taking account all the differences between the abstract problem and the situational problem. So who should be the man and who should be the woman? Who's and it is much more intuitive to me to think the students look for the university's actors, while the universities are the recipients. Why? Well, if you think about it, it'd be easier to accommodate receiving multiple proposals because our algorithm already does that. So, check mark. While proposing to multiple people at once, now that's a bit harder to do immediately, and so pick the simplest solution that's also the most clear, and so we decide that students will be males and the universities will be the females. Now, you can also think of this situation as many, many men and a few dating circles comprised of women and the men trying to enter them. Excellent. So, moving on. Now the next question is, what steps need to be changed to accommodate the situation? So what steps need to be changed? The situation. All right. So this involves going through the algorithm step by step. So first, what's the difference between the stable marriage algorithm and this problem here? So basically, we have a plural number of slots, and we'll see where this plays in here. So everything else is the same. The N students have like the M universities in order of preference. There isn't a multiple list or whatever. So each man goes to the first woman on his list, not yet crossed off. This matches, so we don't have to do anything more about that. Each woman says maybe come back tomorrow to the man she likes the best among the proposals. Now, man is singular in the stable marriage, but here universities have slots, have multiple slots of people that they have to fill. And so you can think of the quota of the women in the original problem as just one. So this situation is actually a bit more general because this allows a quota of the quota depending on the university. Now everyone else trying to get in will be rejected if they're not good enough. So one change you'll have to make is that universities can put multiple students on a string and reject everyone else, basically. Now, what does it mean to put multiple students on a string for a university? Obviously, the university can't just go registering people immediately, so the homework solutions say they go on a wait list. And this is basically just saying we want to project what our students, what our acceptances will look like before they are sent. And this is basically just a technicality fitting the situation. Good. So next we can see each rejected suitor crosses off the woman. So after we reject people, then each individual person plays with his or her own preference list. So this is okay. This matches the original algorithm. And the above loop is repeated each successive day until there are no more rejected suitors. Now, there are more students than university slots, but that's okay. This is the same because every student will get considered as universities try to fit better and better people into their slots. So this is fine too. But one other thing that requires a change is how do we like the best among the proposals? Well, universities, after putting multiple students on a string, those multiple students, all the students must propose again. And what does this allow the universities to do? Can compare all the students on the wait list with the new applicants that come in. So essentially, this is just another technicality which basically says we need to compare not a singular man, but a whole group of students. And so with these two changes, and the fact that you reinterpret this as rejecting until there are no more rejected students, which can outnumber the universities, but the university slots, but every student will still be considered. And until there are no more rejected students and everyone else is on the wait list, basically saying the same thing. So these two changes plus this changed interpretation is the answer to part A. Excellent. I'll pause here. Now part B, carefully state a version of the improvement lemma so that that applies to your algorithm and prove that it holds. So our improvement lemma is very similar to the one that's in the lecture notes. Recall from the lecture notes that for every day, so if a woman finds man M, then on a subsequent day, she has M or someone better on the string. And so the improvement lemma here can be if a university has a group of students Q then on all subsequent days, and this should be all too, the group of students it has will be better or the same as Q of U. And so basically all we're doing is that all the students in the universities, their rankings combined, for instance, will be better than what they found at the beginning. And so to prove this, we just need a proof by contradiction. So consider some university and a day greater than day 2, because like after the you can match with someone after the first day, but you won't do anything much beyond that until you hit day 2 where more people come in. So consider so you assume basically that the improvement lemma is true on day k. Consider day k plus 1. Now what happens here is that when we hit the new day, we will need to do a comparison in the afternoon where the university compares all students on its wait list with the new applicants. And this condition is that the university only keeps the people it likes best. So obviously, the candidates that are entering the university must be at least as good. Otherwise, there's no reason. So candidates kept must be at least as good. Due to the algorithm. So this is basically an inductive proof that proves that our improvement lemma holds. So therefore the improvement lemma holds. And if you, this proof is not very rigorous because I wanted to go through it quickly and just gloss over the main details. If you want a more rigorous proof, please visit the written homework solutions. So this is the answer to part B. Now notice that the only thing that we really needed was for the group of students to be better for all subsequent days. And we'll just use this fact to prove that our algorithm holds. We did all the hard work in problems A and B, so problem C is actually not too difficult. Let's just recall the improvement lemma before we continue with our proof. So each university has a group of students whose cumulative ranking is greater than its students' rankings the day before. This is just paraphrasing the improvement lemma. And so suppose for contradiction, this is very similar to the proof in the book, lecture notes. Suppose toward contradiction that a student did not receive any news, accept or reject when the algorithm terminates. Now this means that the student must have applied to all the universities on his list. And we make the assumption that he has all the universities on his list, but it's given here, ranks the M universities. Now, by the improvement lemma, right? By the improvement lemma, each university has its Q students on a string because the algorithm terminates when basically everything is assigned. So we're assuming that a student was not assigned yet, and we'll see why this contradicts, because in the process of determining this, the QN students or QU students, it must have looked at all the applicants. It must have looked at all its applicants throughout the algorithm, the execution of the algorithm. So the fact that the student, did not get assigned must mean that the student was rejected. Again, the important part is that the university must have looked at all its applicants throughout the execution of the algorithm. So we've arrived at a contradiction based on the improvement lemma. And because the thing is, if it doesn't look at all of its applications, it can't guarantee the second condition here, where the university does make sure it doesn't prefer some unassigned student to what they already have. So they must look through the entire pool. So university must look through the entire pool. To guarantee this condition. Or, or universities must receive applications from entire pool that isn't taken yet of students not yet taken to guarantee this condition. And so because of this improvement lemma and this condition, we have a contradiction that a student is unassigned at the termination. So that means every student must know whether they got accepted or rejected. And that is it for the homework. Congratulations for finishing homework 3.